Hello. Okay, so welcome everybody to today's joint CHEP plus Physics Colloquium. So today we are very happy to have Professor Bharat Ratra visiting us from Kansas State University, where he is a distinguished professor of physics. Professor Ratra did his undergrad in IIT, master's degree in IIT Delhi. Then he received a PhD in Stanford University. He was a postdoc at Princeton, Caltech, and MIT, and then he joined Kansas State University in 1996 as an assistant professor. Professor Ratra has done some leading works on dark energy. More precisely, he and Jim Peebles proposed the first dynamical dark energy models, and he has compared that with data with lots of data and done some high impact work. And today he'll be talking to us about dark energy dynamics, spatial curvature, neither or both. Thank you.
Thank you for that really nice introduction. So before I start, I just want to point out this website. It's got some really nice videos on global warming that can be understood by people who are not experts, so it's worth looking at and promoting. So I'm a cosmologist, and I'm really interested in dark energy and spatial curvature, so that's what I'm going to talk about today. And so I have a pretty long introduction. Are you all pretty familiar with cosmology? Is there anybody here who's not that familiar with cosmology? You can put your hands up. Okay, so I'll try to go over the introduction. I'll go over a little bit faster so I can spend more time on the more technical part. So at the present time, when we look at the energy budget that's driving the expansion of the universe, we know that only about 5% of it is coming from atoms and molecules, and that's what cosmologists refer to as baryonic matter. Approximately 25% of it is coming from something that's not made up of atoms and molecules, but we know this stuff is moving very slowly, and it's not moving at speeds close to the speed of light, and it's called cold dark matter. And it's dark because it doesn't interact with electromagnetic radiation, so we don't see it. If it does interact, it interacts very, very weakly, not as strongly as atoms do. And even more recently, people have discovered something stranger that makes up the biggest part of the energy budget. It's also not made up of atoms and molecules, but if it's made up of particles, these particles are very, very light, and they're moving at very high speeds, at speeds close to the speed of light, and it's been called dark energy. And this is energy, just to distinguish it from matter. This is not energy in the sense of kinetic or mechanical energy. So what I'm going to do is try to motivate this dark energy, and then look at two physically based models as the cosmological constant with cold dark matter and the dynamical scalar field with cold dark matter. And a lot of data analysis is done with parameterizations that are easier to use in the analysis. So ΛCDM is not that difficult to work with, but a consistent dynamical dark energy model is much more difficult to work with. And so instead of using this model, people use W or XCDM or W0 WA-CDM. And they're parameterizing the parameter W as a function of redshift, and this will become clearer a little bit later. So we're going to take these models, we're going to make predictions for things that can be measured and compare to those predictions. And so we'll get constraints on the parameters of these models. And then I'll talk a little bit on the transition from when dark matter and baryonic matter dominated and we had decelerated expansion to the current epoch when we get accelerated cosmological expansion. And then I'll talk a bit about the measurements of the Hubble constant and a bit about spatial curvature and some problems with the Planck PR3 data set as far as excess weak lensing shows up there. And then I'll talk about the newest DESI result. So we're trying to get some idea of what's going on in cosmology, and what we're doing is instead of trying to do this in a model-independent way, because we can't, our data is not that great, so we're going to take a parameterization or a collection of parameters based on physical models and all these parameterized models. And so we'll use maybe 6 or 7 or 8 different parameters and constrain them using the data. And this allows you, if you use physically consistent models, they allow you to get more reasonable constraints because the parameters are consistent with modeling. So we're going to also use these to compare different models and different data sets. And if we use different models and we're driven to the same part of parameter space in terms of omega matter and the Hubble constant, then you can see that your data is independent of what model you're using to do the analysis with. And we can also use different data sets with the same model and see if one set of data is pushing you to a different part of parameter space than another set of data, and that might lead you to try to look for systematic errors. And we can also combine different data sets, different constraints, and get tighter consistency constraints on parameters. So we know the Hubble law. So a galaxy a distance r from us is moving away with this speed, and h0 is the Hubble constant. And then my favorite value is 68 plus or minus 2.8 kilometers per second per megaparsec. And this law holds at all times, but the constant of proportionality depends on what time you're looking at this law, and then it becomes the Hubble parameter, which is a function of redshift or time, and h0 is the current value of the Hubble parameter. And here's a famous plot of the Hubble law. This is from one of the Hubble Space Telescope key projects. And this is their final paper in 2001. It was led by Wendy Friedman. She was the PI on that project. And this is the velocity, the recession velocity of galaxies. These are distances to the galaxies. You can forget the residuals down here. The distance numbers are here. So galaxy 100 megaparsecs away. It's moving away at 7,000 kilometers a second. And this is the Hubble law, the solid red line. So in that same year, my collaborators and I wrote a paper looking at a compilation of Hubble constant measurements. We had about 200 and something, and we did a median statistics analysis. And then in 2011, a graduate student and I repeated that with 553 measurements of the Hubble constant. So the Hubble constant is probably the most measured parameter in physics. And we got 68 plus or minus 2.8 kilometers per second, which is consistent with pretty much almost all measurements of the Hubble constant since then. There's a couple of notable exceptions, and I'll come to one of those. And this is an example of one of the exceptions. So what we're doing here is looking at CMB data on large scales from WMAP and on small scales, and galaxy clustering data. And this is in the ΛCDM model, and we're going to marginalize over all parameters except h0, and we're going to allow the number of light neutrino species to be a free parameter that we're going to constrain from these data. And we're going to use two different priors. They're just going to be Gaussians with the central value and the error bars. So this is 68 plus or minus 2.8, the one we get from median statistics. And then the 73.8 plus or minus 2.4. This is from the Adam Rees group. This is one of their earlier results. They're calibrating on Cepheids and then using supernovae to get into the Hubble flow and measure the Hubble constant. And you can see immediately that the contours are different. The blue ones favor a lower Hubble constant, and they're consistent with the number of light neutrino species we have in the standard model of particle physics, while the red contours are 2 sigma away from the number of light neutrino species we have in the standard model of particle physics. So even in 2011, the standard model of particle physics could distinguish between a Hubble constant of 74 and 68 at 2 sigma. And that's a pretty impressive result, because 15 or 20 years before we didn't know the Hubble constant to a factor of 2. So we know that the universe is expanding, and so we have to be a little bit careful about how we frame things, because there's favored observers, and these are called cosmological observers. These are the ones that are addressed with respect to the expansion. And these are the guys who see that things are isotropic on large scales. And the cosmological principle asserts that all cosmological observers see isotropy on large scales, and that implies that we live in a homogeneous universe, and that makes our life much, much simpler than a universe that's inhomogeneous on large scales, because we can have only 3 spatial geometries, and everybody's seen these plots. So I'm going to suppress one space dimension to draw them here because I can't draw the 3-dimensional ones in all cases. So that's the line element, that's the scale factor, that's the scale factor for the spatial part of the geometry. And you can get closed models like the surface of the sphere, and that's overdense, and the spatial curvature is positive. Or you can get flat models, and those edges have to go out to infinity, because if they didn't, it wouldn't be isotropic as you get to the edge. And that has 0 space curvature, and that's critical density. And then you have the open one, and those also have to go out to infinity, and that's got negative space curvature, and it's underdense. And so I'm not including dark energy here, and that's why these things are the values they have. So we need a dynamical variable, and very loosely you can think of the scale factor as being the radius of the sphere, and as it gets bigger and bigger, the universe gets bigger and bigger. And you get the equations of motion. These are for an ideal fluid model, and you can put in other things also, but I'm just going to write down the simplest equations of motion. So you get the Friedmann equation that relates the expansion rate, so dot is the time derivative, to the various things that are powering the expansion. You have mass per unit volume, or energy per unit volume, the energy density, and spatial curvature contributes, and the cosmological constant contributes. And you also have to have conservation of energy, so the rate of change of the energy density, it's going to do PDV work, and that's why the pressure shows up here. And to complete this, you need an equation of state that gives you the pressure as a function of the energy density. So we know things are redshifted if you can get out of our local group. And so that tells you that the Hubble parameter is positive, and A dot is positive, so things are moving away. The next thing you might be interested in is A double dot, whether this expansion is accelerating or decelerating. And you can get an equation for A double dot by differentiating these and combining them, and you get this equation. And if we ignore the lambda for a second, you can see there's a minus sign over here. This is energy mass per unit volume for cold dark matter and baryonic matter, and this is the contribution from the pressure. And that's the active gravitational mass density. And that minus sign tells you get deceleration. And you can go and measure A double dot, and it turns out that A double dot is actually positive. So you've got a problem. You can either discard this equation and say Einstein was wrong, or if you want to be more conservative and say general theory of relativity works for black holes, and it works for gravity waves, and it works for binary pulsars, and so we don't want to throw this equation away, but we want to introduce an extra substance in here, which we're going to call a cosmological constant, and we're going to give it an equation of state of this form, P equal to minus rho. And we're going to get, so this rho lambda plus 3p lambda is going to be minus 2 rho lambda. And we're going to choose rho lambda to be dominant over rho matter. So then this negative piece can overwhelm this positive piece in here and make everything inside the square parenthesis negative, and that negative sign will cancel that, and A double dot will be positive. And that's why we introduced dark energy, and the simplest one is the cosmological constant. Yeah. So the data sets for the Hubble constant, so it's WMAP the first 7 years, and the small scale CMB anisotropy and Sloan galaxy clustering. And I'll show you this with much more recent data also. The red one is, so these are 2 measurements of the Hubble constant, independent of the data I'm using here. So we're going to just use these as priors. And this is from Adam Rees's group in 2011. So it's calibrated using Cepheids, and then the constraints are coming from type 1a supernovae. So that's why we introduced dark energy, to patch up GR so that it's consistent with the fact that A double dot is measured to be positive. And that would be a silly thing to do if you're just going to fix one observational point by doing this. But it turns out there's half a dozen different measurements of dark energy, and they are all roughly consistent with each other. Yeah. No, the blue thing is, so the blue thing is it's mostly later universe stuff, because we just took 553 measurements of the Hubble constant, and most of the measurements of the Hubble constant are late universe. And I'll show you more recent data. No, it's also got other supernovae, the older supernovae. This is just this one paper, which is basically became the SHOES project, and this is the median statistics analysis of all the Hubble constant data we had in 2011. But I'll come to the most recent data, and we can talk about that, because that's better than 10-year-old, 15-year-old data. So let's see why people think there's dark energy, and the simplest thing is shown in these cartoons. You can look at the Hubble law in two different universes, one that expands more slowly and the other that expands more rapidly. And so if you go and look at a galaxy at a distance d in each of these universes, in the blue universe it's going to be moving away from us slower than it would be in the green universe. And as you go to further and further distances, you're looking at what was happening at earlier and earlier times. And so there's three possibilities. The expansion rate could be constant, and it would be like the purple line. Or as you go back in time, that it expanded more slowly in the past, and as it came to the present, it accelerated. Or it could be that it expanded more rapidly in the past, and as it came to the present, it decelerated. And in 1997 and 1998, the furthest you could go is to make use of type 1a supernovae. And if you did that, you found most of them were in the blue part. And they favored this model, that it was it expanded more slowly in the past and it accelerated to the present. And you've all seen plots like this. This is also an old plot. So it's omega in lambda and omega in matter. And if there was no lambda, you should lie along a line here of omega lambda equal to 0. But the supernovae are forcing you up here. And current supernovae data are giving you dark energy at maybe 4.5 or 5 sigma, so it's a pretty strong signal. So A double dot has to have components in here such that P has to be less than minus 1/3 of rho, and that's dark energy. So we know there's dark energy. Yeah, sorry. Okay. Yeah. So you can see the dark energy in the CMB, if that's the question. You can see it in the CMB, you can see it in BAO, you can see it in other data sets, and so I'll mention some of those. And yeah. 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 So there'd be joint analysis, right? So I don't know off the top of my head, but you can go and see there's an ACT paper now last week where they look at this, and you can probably figure out from that what the size of the error bars on lambda are. Okay, so we know there's dark energy, and we also know that it's the major contributor to the energy budget, but all we're seeing is the gravitational effects of it, and we don't know whether it's a cosmological constant or whether it varies in space and time. And the easiest way to deal with this is to look at different models and compare to observations, but we have to make assumptions that GR is valid and there are no big missing systematic errors, and I think both of those things are true. So I'm going to look at a number of models. This is the standard model, and I'm going to show you these plots. They're at relatively late time, so there's a function of the density of these various things, and it's a log-log plot is a function of scale factor. So we live over here, and you can go back to the early universe, but I'm not going to go back far enough to bother about radiation. So the Friedmann equation is up here. You get a contribution from ordinary matter and baryonic matter, and that's going like 1 over a cubed. That's the blue line. The orange line is space curvature, and the green line is a cosmological constant. So earlier on, when you're dominated by the blue line, or the orange line is a borderline, but when you're dominated by the blue line, you get decelerated expansion. But when the green line is the dominant one, you get accelerated expansion. And it looks like you have 3 independent parameters here, but they're not independent, and we'll see that because we'll see in a second that the sum of the omegas have to add to unity. So there's only 2 free parameters, and conventionally in this model, it's the current value of the matter omega and omega lambda. And you can immediately see what the problem with dark energy is, at least to particle physicists. This is an energy per unit volume, so you can change it to an energy to the 4th power, and if you take the 4th root, that tells you what the energy scale associated with this is. And that scale is a milli-electron volt or so. And until recently, there was nothing fundamental happening there. I mean, neutrino masses are showing up around there, but it's kind of unclear if they're related to dark energy. But so it's kind of a problem if you want to introduce a new milli-electron volt scale here. And it's easy to get rid of that. So one way you can get rid of that is to tilt this line a little bit and make it a function of time. And even a tiny tilt, because the universe is so old, you can start out with the GeV or TeV or even higher dark energy scale. And as time goes on, it drops to the present and generates that milli-electron volt scale. So if you just take a straight line here, sloping straight line, that's called the ΛCDM or the WCDM parameterization. And I'm going to drop curvature for now, and we'll put that back in later, but just to make this a little bit simpler. So you have ordinary matter and baryonic matter, and that's the 1 over a cubed, that's the blue line. And then you have a new fluid with this equation of state, where W sub x is chosen to be less than minus 1/3. And that gives you the slope you need to get accelerated expansion here and decelerated expansion there. And the 2 free parameters in this case are going to be omega matter at the current epoch and W sub x. But you can immediately see what the problem with this model is, because if you take dp d rho, that'll give you the speed of sound squared. And if this is negative, the speed of sound squared is going to be negative. And then the speed of sound becomes imaginary, and it's not stable. So this is not a physical model. In the computations, people arbitrarily usually set the speed of sound to the speed of light there. You can make this a physical model by introducing a scalar field. And then you have the Friedmann equation. You have ordinary matter and baryonic matter. That's the blue line. And then you have an energy density from the scalar field that has a kinetic piece. There's a dot there, so that's phi dot squared. And a potential energy density, and I've chosen an inverse power law potential energy density. Because this is a dynamical field, you've got to introduce the Klein-Gordon equation in the expanding universe. So you get phi double dot plus the Hubble drag term, but dv d phi. And you can't solve these equations analytically, but you can solve them numerically, and you find a really nice phenomenon here. You get attractor solutions, and depending on which epoch you're in, so if you started in the matter epoch when the matter dominates, this guy starts bending and it wants to come to dominate over the matter energy density, and that can help explain why we're coming into a dark energy dominated epoch now. So the free parameters I'm going to use for this are omega matter now and alpha, the spectrum, that index up there for the potential energy density. And so this new energy scale can be much, much higher than an MeV, and it expands, the universe expands and drops it to an MeV. So, yeah. 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 Because the speed of sound is very, very close to the speed of light, the perturbations, if you think of this in terms of particles, they're very relativistic. And so only on scales comparable to the Hubble radius does this stuff start clustering. And so you see it in the CMB, and you can see it also in the BAO, but it's not going to collapse like dark matter does, because those particles are much, much heavier and they're much more slowly moving. So it stays much more uniform up to scales of tens or hundreds of megaparsecs. Yeah. Because it's not a fluid, so there's no P and rho for that. It's just they're both. You don't interpret it as a fluid. It's just a cosmological constant. It doesn't vary with time. But if you have a fluid with a negative pressure equation of state, it's always unstable. Yeah, you're going to have a problem, and it's better to try to use a scalar field, but then you have this extra equation, you have the Klein-Gordon equation, you have to integrate things. But the fluid model you can integrate analytically, and that's why people use that for data analysis. So I look at some old supernovae data and some old baryon acoustic oscillation data and Hubble parameter data and growth factor data. And I'm doing that because the error bars are bigger and you can see what happens more clearly. And then I'll go to the most recent data. So the procedure is you write down the Friedman equation, and you write it down in terms of redshift. And so if this is the lambda CDM model, then you get an omega matter term with 3 parts of 1 plus z, 1 plus z, and omega curvature and omega lambda. And you can see where that sum rule comes from, because if you evaluate this at the present time, the h naught squares cancel out, that becomes 1, that becomes 1, and you get this equation. So you don't have 3 free parameters, you just have 2. And conventionally they're taken to be the matter density, omega matter now, and omega lambda. And this equation can be rewritten in this form. It gives you the Hubble parameter as a function of redshift, as a function of the cosmological parameters, as a function of the Hubble constant. And so you can go and look at what redshifts you have measurements at, and then make predictions in this model, and then use whatever technique you want, maximum likelihood or chi-squared, and constrain the cosmological parameters, the parameters P. So I'm going to show you a lot of plots like this. There'll be 3 of them on each page. There's going to be lambda CDM in this corner, X CDM or W CDM over here, and phi CDM over here. The x-axis is always going to be omega matter now. The y-axis in this case is omega lambda, W sub x, and alpha, which is the parameter in the power law of the scalar field potential. And there's 2 special sets of lines. There's the dashed lines and there's the dotted lines. So the dotted lines divide currently accelerated expansion from currently decelerated expansion. And you can see those over here. And this line is flat geometry. So models this side of the line are closed, models below it are open. This line is Wx equal to -1, so it's the cosmological constant. And because this is spatially flat, this line is identical to this line. And I'll come back to that in a second. And alpha equal to 0 also corresponds to a cosmological constant. So if you pick any value of omega matter, say 0.3 on this line, that's identical to the model here at omega of 0.3, and it's identical to the model here of omega 0.3. So you can see this is type 1a supernovae data from a decade or a decade and a half ago. And you get 3 sigma contours, 1 sigma, 2 sigma, 3 sigma, 1 sigma, 2 sigma, 3 sigma, 1 sigma, 2 sigma, 3 sigma, and the best fit values. And you can see a whole bunch of things very immediately. So first of all, in all cases, you're mostly in the accelerated part of parameter space. So it doesn't matter what model you use to analyze these data, you always end up with currently accelerated expansion. You can also see the standard model with omega matter of 0.3 spatially flat and omega lambda of 0.7 is pretty much right in the center. And it doesn't matter what model you use to draw that conclusion, because omega matter of 0.3, and that's flat lambda CDM over there. And the best fit point is over here, so omega matter of 0.3, it's right over there. But there's also lots and lots of room for spatial curvature and dark energy dynamics. And we can go through this relatively quickly because this is older data, it's not that useful. But if we look at BAO, you see the same sort of things. Most of the probability is in the accelerated part of parameter space. They're all consistent with the standard model. And there's lots of room for space curvature and dark energy dynamics. But probably the most interesting thing is that these contours are aligned this way. And if you go back over here, they're almost perpendicular to these contours. So if you do a joint analysis, you're going to end up with much, much tighter constraints. So you can look at Hubble parameter data. And here, because the predictions depend on the value of the Hubble constant, you get 2 sets of contours. The solid lines are that 68 one, and the dash dotted lines are the 74. And so they move by about half a sigma. But the same thing's true. The standard model is right in the center pretty much. And there's lots of room for space curvature and dark energy dynamics. And the same thing's true here for growth factor, but the contours move around. So the really important thing is that there's huge parts of parameter space that overlap for these different data sets and for the different models. So we're not completely crazy introducing dark energy. The individual data sets are all consistent with the standard model, but they don't yet rule out dark energy dynamics or spatial curvature. And so you can do the obvious thing, combine 2 data sets at a time. And if you do that, the parameter space that's allowed becomes much, much smaller, but the conclusions are the same. The standard model is very consistent with these data. And there's lots of room, well, not as much as previously, but there's still room for space curvature and dark energy dynamics. And it doesn't matter which data sets you use. So 2 at a time, they give you tighter constraints. They're all consistent with the standard model. But there's room for dark energy dynamics and spatial curvature. And if you look at this more closely and look at different supernovae data, you get the contours moving by half sigma, 3/4 sigma. You use different GRB data techniques, and you get different constraints. And so maybe that's the problem with GRBs. So the different values of H we use move the contours by half sigma. So there's a bunch of systematic effects. And the data is getting bigger and better. And so we can draw some interesting conclusions. But before I get to that, let me just change gears for a second and look at the Hubble parameter. The expansion rate is a function of redshift. So there's enough data, and this again is from over a decade ago, and this comes from cosmic chronometers or radial BAO measurements. And it looks pretty messy, but these models in here are the 6 best fit models. And there's 6 of them because we're using lambda CDM, X CDM, and phi CDM. And we have to choose the value of H naught. So some of them are giving you 74, some of them are giving you 68, and you can kind of see they converge there. But these are the 6 best fit models to these data. And these are the 2 most extreme 3 sigma away models. And you can see that the best fit models have this dip here. And it becomes a little bit clearer if we bin these data in redshift space. We can't do that at higher redshift because it's not dense enough. But if we do that, then with 2 sigma errors here, so that's 1 sigma, 2 sigma, you can see the dip here. You can see decelerated expansion at higher redshift when ordinary matter and dark matter dominates, going to turn over into accelerated expansion at lower redshift. Where the cosmological constant kicks in. And this is an old analysis, so there's other error bars now, but this gives you the transition redshift at about 3/4 when you go from matter dominated to dark energy dominated, and you can see the transition. So now I'm going to change gears and look at the most recent data, and I'll start out without using the cosmic microwave background. So the data I'm interested in are BAO, Hubble parameter, Pantheon plus supernovae. So that's redshift about 2.3, redshift about 2. That's the highest redshift data points, and that's again redshift about 2.3. And most of the constraining power is in these guys, but a little bit is coming from these newer data sets. There's angular size for quasars. There's reverberation mapping quasars for the MG2 line and the C4 line, and I'll talk more about that. And there's also gamma ray burst data. And the correlations I'm using for that are the Amati correlations. So these guys go up to a redshift of about 2.7. This goes to a redshift of 1.9. That's a redshift of 3.4. That's a redshift of 8.2. And I'm going to do this BAO analysis without using the Hubble, the CMB sound horizon at drag epoch. I'm going to do this by allowing omega B and omega C, omega matter, omega B and omega C to be the free parameters instead of just omega matter. And then you can compute in the model the Hubble, the sound horizon at drag epoch. Yeah. Yes. So we have a bunch of papers, and I'll talk more about this in a little while. So we're going to look at this with 6 different models, and we'll marginalize over all parameters except H0. So this is a measurement of H0. If you just focus on this model, it's a measurement of H0 that assumes the lambda CDM model, and it's completely independent of the CMB. It's completely independent of local calibrators like Cepheid, so tip of the red giant branch. And so that's what you get. You get 69.5 plus or minus 2.4. But if you look at it in all 6 of these models, they're all consistent with 69.25, and there's a statistical error of about 0.3 plus or minus 0.3. Sorry, a systematic error of plus or minus 0.3, because it goes from 69.5 to 68.9. That's the range, so it's 0.6. And you can call that twice the statistical error. And systematic error. And this is a statistical error. It's plus minus 2.4. So if you add that in quadrature and then take the 2 central points, 69.3 and 69.2, and average them, you get the 69.25 plus or minus 2.4. And this is independent of the cosmological model because the difference between them is plus or minus 0.3. So, yeah. Independent of what, CMB? No, supernova without the Cepheid calibration. So I'm using uncalibrated Cepheid supernova data. So you know the distance because in a given model, you can compute the sound horizon at drag epoch if you know omega B and omega C. So I will let omega B and omega C be free parameters, constrain those parameters from these data. And so I'm getting that distance from these data by themselves. That's why these error bars are plus or minus 0.24. That's why they're pretty big. Yeah, I'm measuring the distance in a model-dependent way, but there's almost no difference. It's so small. So, I mean, that's it contains the Pantheon plus supernovae, but it does not contain the Cepheid calibration or the tip of the red giant calibration of those supernovae. With which one? So that's what I'm going to go over right now. So I get 69.25 plus or minus 2.4, and this is very, very consistent to our results from almost 15 years ago from median statistics. So this is very nice paper by Wendy Friedman's group, and it's well worth reading if you want to really understand her view of the Hubble tension. So she gets 70.39 plus or minus 1.94, and this comes from both JWST and Hubble Space Telescope tip of the red giant branch data, and she gives it to you as statistical errors, systematic errors, and then errors in the supernovae, because she calibrates the supernovae using the tip of the red giant branch. And I've just combined those errors in quadrature, and that's why I've got plus or minus 1.94. So Adam Rees's group, where he calibrates using Cepheids and type 1a supernovae, gets 73.04 plus or minus 1.4. So there's a difference at these two redshift, low redshift ones of 1.2 sigma difference in the Hubble constant. And if we compare this number with these 6 numbers, our values are between 1.3 and 1.6 sigma lower. So it's not a big effect, but it would be really nice to try to understand why there's this difference here that's of the order of somewhere between 1.2 and 1.6 sigma. And then what people usually call the Hubble tension is the difference between this number and this number, which is from Planck. And you can see that so Planck assumes a flat lambda CDM model. And if you look at our flat lambda CDM model value, our value is about 0.9 sigma higher. So we're coming in a little bit higher than Planck and a little bit lower than the Cepheids. And we completely agree with the tip of the red giant branch. And it might also be relevant that these two other groups for the CMB, small-scale CMB, ACT, and SPT also come in around 68. So that's my view of the Hubble constant. So the next thing I want to talk about is the space curvature. So people keep saying that the CMB gives you 0 space curvature. It doesn't, because Planck by itself actually favors about a really small amount of closed geometry at about 1.6 sigma when they use a cosmological constant. But when they combine Planck with BAO, it becomes, yeah. Yeah. I haven't looked at those because I would prefer to stick to Pantheon because it's spectroscopic, and the Union ones and DES, they have a lot of photometric also. So it's an interesting question, but I think you'll find differences, but I don't know if it'll be that significant. So it's interesting to see what happens if you analyze these data with very dynamical dark energy instead of using lambda CDM, and then we can do dynamical dark energy and non-flat models. So that's what I want to move to first, and then we'll go back and look at other things later. So I'll go back to this ΛCDM parameterization. So previously we had the blue line and the green line. I'm going to put in the orange curvature line. And we'll have 3 parameters now because I've introduced curvature. So I've added the value of the curvature now. And in phi CDM, I'll do the same thing. I'll put in the orange spatial curvature line. And I'll just tell you the results. Again, it's from these data sets. And these give you most of the statistical weight. And we carefully checked these contours from each of these data sets individually, and we find that they're consistent, and we've actually discarded a lot of data. So some of you might be familiar with X-ray UV correlated quasars, and we can show that those guys are not standard candles, so we don't use that data. And we also looked at reverberation measured H beta quasars, and we can show that those are not behaving consistently. And we looked at H2 starburst galaxy data, and we can show that those are also not standard candles. So if you do this with these data and those 6 models again, you're getting mostly consistent with flat geometry, at most deviating by a little more than 1 sigma. But there's a stronger signal for dark energy dynamics, somewhere between 1 3/4 and 2 1/4 sigma. But these are all pretty small, so you can't really conclude that much. So the reverberation map quasars is one possible probe. And so the way this works is you get the light from here, from the black hole, so that's the torus, and that's the broadline region, and then you get light from here, and you can then measure the time lag that you're assuming that the black hole is creating all that power and then it's lighting these guys up, so you can measure the time lag, and that's this variable tau. And you can see that if you assume a correlation between the time lag and the absolute luminosity, that these data do give you a reasonable correlation. The correlation is significant. So the time lag can be measured really easily, and that can then, you can use this RL relation to get the absolute luminosity. And so far, in most of these cases, except for H beta, we're finding that there is a good correlation, and these are standardizable candles. But we're using 50 to 100 of these at a time. And it's not clear this is going to survive with bigger data sets, but Rubin Observatory, LSST, should get 10 to the 4 or 10 to the 5 of these, and that's going to be a big enough data set to use. So I'm going to now change gears again and look at the CMB in non-flat models. And we'll start out with lambda CDM with spatial curvature. And usually you assume this Harrison-Peebles Hughes-Eldovich spectrum of k to the n for the fluctuations. And that assumption is based on this curvature not being there, and that there only be one scale, and that's the Hubble scale. And so it's not fair to make that assumption, except in the spatially flat case. So if you want to redo the computation in an inflation model that's closed, you can get the harmonics and do the analysis, and you get a bunch of messy results. So it's been known since the 90s that in slow roll inflation models that are closed and open, you can get a more complicated bar spectrum. So the the eigenvalue of the spatial Laplacian in the closed case is A times A plus 2, where A runs from 2, 3, 4, 5, and so on. And Q is typically A plus 1. And this guy is the power spectrum you get in slow roll inflation models. But we know that this is not tilted. And so when Planck did their analysis, they took our slow roll inflation model's power spectra and multiplied it by k to the n minus 1 without providing much motivation for that. And I'm working with some collaborators and trying to understand whether you can get a spectrum like this from inflation models, and we find with numerical analysis that you can get something pretty close to it. And I also looked at open and closed inflation models with more complicated potentials that are functions. So C is a constant, it's not the speed of light, phi is the inflaton, that there are powers, inverse powers of these guys. And I don't want to show you the analytic expressions, but you can see, say in the open case, so in the flat model, the matter power spectrum is this blue line, and the red line is the power spectrum I computed, and this dotted line here is the power spectrum from the Planck analysis. And you can see the differences. They're out at very, very large scales, so there's going to be issues with cosmic variance, and so even, yeah. Right. A curvature scale. Right. So So they put it in ad hoc. So you can compute these spectra when you have very slow roll inflation, and you can get analytic expressions, and they're both of this form for the open and closed case. And so they just took that, and they know it's untilted because it's very slow roll, and they multiplied it by k to the n minus 1. So that was their prescription. So it turns out that you can go and look at more complicated inflation models. So we've only done this for closed models so far. And we've done this, so I'm working with this with Alan Guth and one of his ex-postdocs, Mohammed Namju. And we should have a paper on this in a month or so. But it's all numerical, and you can show that it comes very, very close to this form that Planck assumed. But the power spectrum I have doesn't get to that form. So it turns out that in non-flat models, you have extra freedom, and you can have different power spectra, and there's nothing that forces you just to a scale invariant form. And so I'm going to just analyze these. So I'm going to use a bunch of different data. So I'm going to use 2018 Planck data, the TT, TE, EE, and the low E. And I'll also use the lensing potential power spectrum. And for my non-CMB data, so I'm not going to use any DESI data in any of the analysis here. I'm going to use BAO, so there's 16 measurements, and there's 4 of those with growth factor, and 9 other growth factor measurements, and Pantheon Plus supernovae 1590 measurements, and Hubble parameter measurements, 32 of them. And I'm going to show you results here for 12 different models. So it's going to get a little messy. The 12 models are, so we have 2 different forms of dark energy. There's lambda and X. And there's going to be 6 lambda CDM models, 6 X CDM models. So there's 3 different power spectra. There's the flat, tilted, k to the n, the non-flat, tilted Planck version of the power spectrum, and the non-flat, tilted my version of the power spectrum. So that gives you 3 of these and 3 of these. And the other thing I'm going to do is I'm going to introduce this lensing consistency parameter. So in this data release from Planck, some of the C sub Ls seem to be smoothed more than you would expect if you use just the flat lambda CDM model that best fits these data. And so people think there should be more weak gravitational smooth lensing of the CMB than in the flat lambda CDM model that best fits these data. And what this does is it allows a consistency test. So you introduce this as a free parameter, and it parameterizes the amount of gravitational lensing. And at the end, you hope that it comes back and tells you capital A sub L is equal to 1. But it turns out that with this analysis, it gives you capital A sub L that's about 2 or 3 sigma higher than 1. And I'll show you the results. So I'll start out with the lambda CDM model with A sub L equal to 1. And we checked for consistency between the contours from P18 and the non-CMB, and then P18 plus the lensing data and the non-CMB. And our threshold is that if these deviate by more than 3 sigma, then the data sets are inconsistent in this model, and you have to throw away the model. So in the flat lambda CDM model with A sub L equal to 1, they're all within 3 sigma. There's a difference depending on the power spectrum. For this, there's some things that are approaching 3 sigma inconsistencies, but they don't exceed it, so we'll keep them. And here, none of them get close to 3 sigma. So that tells us that we can jointly analyze these data, and if we jointly analyze these data together and marginalize over everything and measure omega curvature, we find that it's completely consistent with flat geometry, and it's actually favoring open geometry by a tiny amount, not closed. So if we put back in A sub L and allow that to vary, the inconsistencies get much, much smaller. So it's insignificant in the flat case, and it's pretty insignificant with the non-flat cases also. So you can jointly analyze these data, and if you analyze that data set and measure space curvature, you get it even more consistent with flat geometry. But A sub L is 2.4, 2.5 sigma greater than 1. So lambda CDM with curvature is forced to flat geometry, but in this Planck PR3 data, that's the P18 data, it's also called PR3, it wants more lensing than the standard lambda CDM model predicts that best fits these data. You don't see this effect in ACT or SPT data because, I mean, the previous ones, I haven't looked at the most recent ACT paper, but the previous ones, they had bigger error bars, and so they were completely consistent with A sub L equal to 1. And there's also a new Planck data release, PR4, that's been released by part of the group. And that has, it's consistent with A sub L equal to 1, but it does show a little bit greater than 1 A sub L at maybe 0.75 or 0.8 sigma. So if you go to XCDM and start out with A sub L equal to 1, you find 3 and 4 sigma inconsistencies, so you can completely throw these models away. And what's happening here is the Planck data, the P18 and the P18 plus lensing, is favoring phantom dark energy pretty significantly. It wants omega to be less than -1, while all the non-CMB data together is favoring quintessence dark energy, and it wants omega to be more positive than -1. So it wants it to be quintessence-like. So, I mean, these models are ruled out. So you can go in and put in A sub L as a parameter and let it vary. And then we find that they're no longer 3 sigma plus inconsistent. So you can then jointly analyze these data. And you find some mild evidence for non-flat geometry in this case. It's only about 0.8 sigma. But a little bit more interestingly is that these favor quintessence dark energy. So the C sub Ls, the Planck data is being overwhelmed by the non-CMB data and the determination of omega. That's true in most cases when you're doing dynamical dark energy. The non-CMB data, when jointly analyzed with the CMB data, tends to dominate in the determination of omega. But it wants omega quintessence-like at 1.5 sigma significance. But again, it wants more gravitational lensing than you find in the best fit models. So that lensing thing comes back. But the important thing is that XCDM Planck data favors phantom-like dark energy, while non-CMB data favors quintessence-like dark energy. So if you remember that, and we go and look at this DESI result, so this is all the numbers here are comparing to the first DESI paper from last year, middle of last year. I haven't use the new DESI numbers. I've looked at the new DESI paper, but not greatly in great detail, but I don't think their numbers change significantly from their first paper. So what they use is a equation of state parameterization of this form, omega naught plus omega A redshift divided by 1 plus redshift. So you can see at redshift equal to 0, this term goes away, and you get an XCDM model where x is W naught, and at redshift equal to infinity, these two terms combine, and you get another XCDM model, but x there, W sub x is omega naught plus omega A. So this has extra freedom, and it can introduce a bend because of the two parameters, but at high redshift where the CMB dominates, it's an XCDM model. At low redshift where the non-CMB data dominates, it's an XCDM model. And so if we use our data and not the DESI data, we get these numbers that are completely consistent with the DESI numbers. 2 sigma, a little bit, maybe 2.5, 2.25 sigma away from lambda CDM. And well, this is probably a better way to say it. It's about 2.2 sigma away from lambda CDM. And you can see what's happening here if you focus on this panel, which is omega A, omega naught. And the red contours are the CMB data, and they're forcing you into the phantom part of this plot. And the gray contours are the non-CMB data, and they're forcing you into the quintessence part of this plot. And the discrepancy between, it's no longer, you don't have these huge discrepancies between those two data sets. They're typically about 2.2, 2.3 sigma. So it's fair to combine them jointly, and then you get these blue contours over here. And if you can, I mean, this is published, this one's published, but it's an archive. And you can see this is tighter than even the DESI contours. And it gives you, favors flat omega naught omega ΛCDM more than the DESI data does. But this is not coming from the DESI data because our data sets that we use to get this don't contain DESI data. And we've also redone the analysis by throwing away the Pantheon plus supernovae data. And so this 2 sigma support for dark energy dynamics is not coming from that supernova data set. So what we did next was introduce A sub L again and redo the analysis. And you can see that evidence for dark energy dynamics drops to, depending on how you define it, to maybe 1 1/3 sigma from 2 1/4 sigma. And what's happening is that the A sub L freedom allows this to overlap a little bit on the quintessence side. The CMB moves to the right, and the non-CMB is over there. You cannot see the gray that clearly over here, but it doesn't change a huge amount, and the blue does overlap now with at about 1 1/4 sigma with the lambda CDM point. So it could be that what these guys are seeing in DESI is that there's this excess gravitational smoothing of the CMB is what's driving this. And they have this model. This is not really a model. This is a parameterization. It's not a physically consistent. It's not a physical model. And so I think it's a little bit dangerous to use such parameterizations for these analyses. And I'm running over time, so I'll skip that and just go to my summary. So I guess current data allows for mild dark energy dynamics. The universe is probably flat, but it's probably useful to try to understand non-flat inflation models better. And it's kind of unclear whether this is just a problem for the lambda CDM model or just for the Planck PR3 data set, and that's going to be an important thing to resolve. And I should probably stop here. Thank you. It's probably better for people in the back. I don't think it's on. This is. Yeah. So the first set of contours I showed you, I had flat geometry for the older data that I used because I did not. So this is the one where I put back space curvature. In the first set, I didn't have space curvature. So the curvature doesn't depend on alpha. So those are independent things. So alpha controls dark energy dynamics. Yeah. It doesn't, I mean, because you're marginalizing over it, and there's a tiny shift in it, but it's not a significant effect. So if you want to just constrain H0, you've got to marginalize over all possible allowed alphas. And it does, the contours do, there's some difference. You can look at the paper, and you can look at the H0 alpha panel, and you can see how it changes. Thank you.